This is a problem using Faraday's law. It's the farmer stealing power from the power company. So let's draw the picture here. We have two supports for a high voltage power line. And in this line is the current, the AC current, given by I0 sine omega t. Now below this high voltage wire, the farmer strings his loop. And the width of his loop is 0.5 meters. And the distance from the wire to one edge of the loop is 5 meters. And it's this length of the loop that we're trying to find. So the farmer would then take the electricity from this loop to his house. Now, the Faraday's law says that the induced EMF in that loop is equal to negative N d phi dt. So it means if there's a changing flux through that loop, there will be an induced EMF in the loop. In our case, N equals 1. So we need to calculate the magnetic flux due to that high voltage line at the location of the loop. The equation for magnetic flux is the integral of B dot dA. Now we do have to integrate this because the magnetic field from that high voltage line is changing in space. It doesn't matter if it's changing in time, but it's definitely changing in space. And the magnetic field due to that long straight wire is still mu naught I over 2 pi r. Even though I has time in it, the equation for the magnetic field still holds. So we're going to place that into our integral for flux. And we get the magnetic flux is the integral of mu naught I over 2 pi r dA. Now dA is the small area element that we have to divide our loop into in order to integrate. So our dA will be strips parallel to the length of the wire because the flux through those strips will be constant. Even though it's changing in time, it'll be constant in space. So let the thickness of the strip be dr, distance from the wire r, and we can see that then dA is equal to the length L times the width dr. So that's what goes into our integral for dA, L dr. Now, the limits of integration for that are the limits on r, so it goes from 5 meters to 5.5 meters. Now, everything that does not depend on r can come out of that integral. Even if it does depend on t, that doesn't matter. So we have mu naught I L over 2 pi integral of dr over r from 5 to 5.5. And so we just pick up a ln in the expression for flux. The ln of 5.5 over 5. Okay, now that expression for flux goes into Faraday's law. So we have the EMF is negative d by dt of that entire expression. Mu naught I L over 2 pi ln 5.5 over 5. Now, when doing a derivative, everything that does not depend on time can come out of that bracket. So we have the mu naught, the L, 2 pi, and the ln all do not depend on time, and we're left with di dt, the only variable that depends on time. Okay, so I is equal to I naught sine omega t, so the derivative of the sine is a cos, and so we have I naught omega cos omega t, where I've just used that the derivative of I naught sine omega t is I naught omega cos omega t. Okay, now that is the voltage in the loop of wire as a function of time. In order to get the peak voltage, we have to take the cos to be the peak value. So this is maximum when the voltage equals the peak. Okay, so I can just let that be 1. Or in fact, I can let it be -1 and get rid of the negative, and it doesn't really matter. So we're left with the peak value is related to I naught omega. Okay, so we're trying to find L, so let's solve for L. L then would be 2 pi peak voltage divided by mu naught ln I naught, and I'm going to put 2 pi f from omega. Subbing in all those values, I would have 2 pi times 170 volts over 4 pi times 10 to the minus 7, that's mu naught. Then the ln I naught was 10 kiloamps, 10 times 10 to the 3, and then 2 pi, and frequency was 60 hertz. And if you sub all those values in, you get, in fact, that the farmer's loop has to be 2.37 kilometers long, an extremely long loop.